Hello, I'm Barry Morris, CEO and founder of NuoDB, and I just want to spend a bit of time giving you an overview of the product, how it works, and some of the extraordinary things that it can achieve. Let me just kick off by pointing out that my co-founder, Jim Starkey, who's one of the grandfathers of database technology and has been building systems for something like 30 years now, has described what you're about to hear as the biggest breakthrough in database technology in the last 25 years. So it's something quite special, and I think you'll be impressed at what we're about to talk about. To start with, let me just talk about, people always ask us, why the bird? Why do we have the green bird logo? And it's to do with the fact that this is what we call an emergent database. If you look at a flock of birds, you'll notice that they behave intelligently as a group. They take off together and they land together and they fly somewhere useful together, even though no one's in charge. And that's what we call an emergent behavior. The individuals are just doing some simple things, but the group does something which is quite organized. And that's in fact what we're talking about in terms of how this system works. It's actually the opposite of what you're used to with SQL and transactional databases. It's a whole new kind of database. Having said that, let me just step back and talk a little bit about the market. Over the decades, there have been different database architectures, starting with the mainframe architectures for databases that ran on big mainframe computers, notably from IBM and others. And of course, those databases didn't make it across the system architecture divide when client server was what was required, and some startups called Oracle and Informix and others took over and really became very popular in the context of that new data center architecture. We're now facing another such change, of course, and that is what we could call the elastic cloud, by which we mean a lot of machines that are shared nothing machines in a heterogeneous environment, lots of small machines, they might be blades or beans or whatever you want to call them, and in which the performance of the machines in the cloud is improved by just adding more machines. That's what we're used to with cloud computing. It's actually very difficult to do with traditional database technology, and so we're going to see the emergence of a new kind of database which has all the same characteristics that you're used to of powerful query languages and transactional semantics, but has the ability to scale out on commodity hardware. So we think SQL's cool. SQL is the language, the de facto language of databases. Upwards of 90% of all database systems out there are running SQL. Not that it's the best query language that we could invent, but it's good enough and it's everywhere. It's what you have in terms of the skills of your people. It's the tools that you're using, the ETL tools, the reporting tools, the development tools, and so on. And it's your business processes. The way that SQL works is tied very much into what your customer, how you think of your customers, or how you think of your products, or whatever. And the same thing goes for asset transactions. It's a very powerful concept. There's something which are at the root of how people run their businesses. And in fact, can you do database work without asset transactions? Yes, you can, but it's much more complex, it's much more painful, puts much more work in the hands of application developers. And you'd rather not do that, you'd rather push that down into the database, which is why they were invented in the first place. And we'd say thirdly that one of the big breakthroughs of the whole relational revolution in the 80s was the separation of data from application, that applications no longer owned the data, that it was separately owned by the organization, and that the organization is able to access that data and do useful things with it independently of the application. All of those things are great, they're cool. The systems that implement this are very powerful systems that have done well for the past 30 years. So we want to keep that. But the problem is that traditional databases actually don't work very well on the elastic cloud. And there are 5 key areas that I'd want to talk about. There's some others as well, but there's some very key ones on this slide. Let me talk you through them. First of all, elasticity, by which we mean that in order to get the system to go faster, you simply add more of these small machines. And if you're underutilizing those machines, you can take some away. So you can scale out and scale in as compared to scaling up, which would be the normal way of doing things. To put that a different way, with a traditional database, the only way you can make it go faster is to buy a bigger machine. That's not what the cloud is about. The cloud is about lots of small machines and being able to add them and take them away according to demand. Virtualization is really, you could think of that as utilization or as multi-tenancy. It's about how can you best utilize some number of machines. Perhaps you've got 100 machines and you've got 1,000 databases. You want to mix and match. You want to be able to assign different databases to different machines at different times and have databases sharing machines where it makes sense. That, if you want to call it virtualization, is something which is at the core of the economic leverage of the cloud. It's why the cloud makes sense from the perspective of saving money. And, or to put it differently, traditional databases are typically run on very low utilization of the machines in the data center. Perhaps less than 10% would be a common number. Virtualization and this kind of utilization of the cloud is a very important capability that just isn't very well supported by traditional SQL databases. Thirdly is the area of extreme availability, and what we mean by this is not something which is in the area of make sure you're running 6 days a week, but more along the lines of something that's running for the next 10 years, and you need the ability to be able to upgrade. You need to be able to upgrade hardware, upgrade software. And you also need the system to be very resilient to failure. It needs to be the situation that if a machine fails or a number of machines fail or an entire data center fail, that the system keeps running. And that extreme availability is something which is part of what cloud computing is about. Unfortunately, it's not something that was built into the traditional SQL database architectures. The fourth key area is what you might call geodistribution, which is about running in multiple centers at the same time, not in a master-slave configuration, not in a disaster recovery type of failover situation, but in which the database is active in both locations or in multiple locations. You could call that active-active operation. And for people that really care about business continuity, running in a geodistributed fashion is very important. It's also very important for people that care about performance, and in particular latency for users. They want to be talking to a part of the database that's local to them, not going across a wide area network to do so. And so geodistribution is very important from that perspective as well. And lastly, in terms of things that are very hard to do with traditional SQL databases, is the very low database administration costs that are inherent to cloud computing. And so you've got the need to run multiple databases you've got a need to be able to run your databases with very little management from database administrators. So we've got a situation in which SQL is a great thing, clouds are a great thing, they generally don't come together. You probably knew I was going to say this, which is that NuoDB solves that problem. It gives you all of the benefits of traditional SQL databases. It can do architecturally, it can support any of the things that you can do with a traditional SQL database. In addition, it does these magic things that we care about in the 21st century, which you might call cloud computing types of things. Before we go into how it does it, let me talk a little bit about the fact that it does do it. And so what you see here is a benchmark, and it's a standard benchmark. It's from it's called the pole position benchmark. You can download it at polepars.org. And what we're doing is comparing a single node of NuoDB. Now remember, this is a database that's designed to run on lots of machines. And here it is running on one machine, and being compared to a database you're probably familiar with, which is MySQL 5.1, running with the InnoDB storage engine. MySQL 5.1, of course, is a fairly highly tuned and optimized database system. What you're looking at is that the little blue bars are us, that's NuoDB, and they're normalized to 1, and the red bars are MySQL. And at the top of the screen you see relatively simple things, which is reads and things like that, those kinds of transactions. At the bottom you see more complex deletes. In fact, that's a deletion of a large inheritance hierarchy, if you can read it. And the message really is that NuoDB on a single node is 2 to 20 times faster than MySQL. On this particular test, this is on a particular day in our laboratories. I'm not claiming that this is some kind of definitive benchmark, but directionally it shows you what you've got is a database that's very fast on a single node. Of course, the point is not to run on one node, but to run on multiple nodes. And what happens if we add a second machine? Well, if you take a look here, you'll see a step function. Prior to that, we were running at about 2,500 transactions a second. You add the second node, and instantly you get to something in excess of 7,000 transactions per second. There wasn't any taking the system down and reconfiguring it. There wasn't any partitioning of the database that happened. You simply added a second machine, and it went a lot faster. It actually goes more than 100% faster in this case, and that is actually a caching effect, which I can explain in a few minutes. Before I do that, let me just point out that if you take that node away again, it simply goes back to what it was doing before, and so it's completely resilient to the loss of that second node. But what may be more surprising is you can take away the first node, and it'll go back to that same performance level. The point here, if you think about the flock of birds we were talking about earlier, is that these two machines are in fact equivalent of each other. They're peers. They're like two of those birds. Neither of them is in charge of the other. Neither is a master. Neither is a slave. And so it's a completely peer-to-peer system. You can add nodes. You can take nodes away, and you can see this kind of performance improvement. Of course, two machines isn't the point either. You might want to run on a lot more machines. Here's an example of us running the same benchmark on 9 machines. And it's a little bit more complex to understand, but if you look at the table in the top left, you'll see that MySQL in this case is running at 3,000 transactions per second. 9 nodes for NuoDB is running at 27,000 transactions per second. I want to re-emphasize, we didn't take the system down and reconfigure it. We didn't repartition the database. We didn't add some sort of cache. We didn't do anything funky. We simply added more computers, and it went faster, a lot faster. I'll also point out, if you look at the bottom left of this chart, that this particular test is not just pure read loads. Those are much easier, of course. This is a load which is 50% updates, and it's still growing at something which is a close to linear kind of level. Looking at the chart, you might say, well, how many more nodes can we add? And we think, we're not quoting numbers at this stage, but we think that we're going to be able to scale this fairly readily to somewhere between 50 and 100 nodes, with obviously very significant performance improvements as we do that. So it's a very fast database. Not only that, but it's elastically scalable. You can add nodes, you can take nodes away. That's all very impressive, and I want to re-emphasize that this is a standard SQL database. So you can take your favorite tools. In this case, it might be Squirrel SQL, which is the most widely used browser for SQL databases. That works. So do Microsoft tools like Excel. So does DB Visualizer. So does LibreOffice. So do a whole lot of other things that our users are asking us to support. It can do that because it's standard JDBC, standard ODBC. It just works. So I guess you've got to ask, well, so we've got something which is a standard SQL database and supports all your standard tools, but it also does this elastic scalability, which is kind of magic. If you're familiar with databases and traditional databases, what we're saying sounds like science fiction. So how does it work? And I'm going to spend a few minutes explaining that. Let's start with the key idea, which is that we've thrown away everything that you know about databases. The top layer of the system is a standard SQL layer, and it looks very similar to SQL layers you're familiar with. But below that, the traditional databases have all got a 30-year-old architecture, which is to do with managing a table-structured file on a disk. And that architecture is monolithic, it's centralized, it's synchronous, it doesn't scale. And that's the problem that is well known in the industry. We've thrown that all away, and we've replaced it with this thing we refer to as emergent architecture. Again, think about the birds. What's going on under the covers here is a set of distributed objects that we call atoms, and those atoms are like the birds in the flock. Those atoms are peer-to-peer, they're asynchronous, and they're communicating with each other, and they happen to be delivering something which amounts to being a SQL database. So what's emergent about the architecture is that the database behavior is something which emerges from the behavior of these objects as they communicate with each other on a peer-to-peer basis. Let's look at the system that we tested first. If you look at that first benchmark that I showed you, where we were comparing our system against a standard MySQL system, everything inside the gray box is us. This is a baseline system. I'll explain to you what's going on. On the left-hand side, you have a thing called a broker. That's pretty simple. It's basically a load balancing system. You've seen those before. On the right is something more interesting. That's what we call the archive manager, and that stores the data on the disk. It's the only place that we store data on the disk. The archive manager is in fact a key value store, and you can use any key value store. Right now it's implemented using the standard file system. It's implemented on top of Amazon S3, and there's some other key value stores that we're going to support over time. But what it knows how to do is to create a blob and to delete a blob and to retrieve a blob. By blob I mean just a big piece of data. I don't mean necessarily something that is formally a SQL style blob. Just any big piece of data, it knows how to put it on the disk and get it back. The thing in the middle is the interesting piece, and this is what we call the transaction manager or the transaction node. It's a diskless node, and this is the thing that manages those objects that we talked about. So the top layer of the transaction manager is the SQL layer. Below that you have these objects we call atoms, and those atoms are what does all the work in the system. I'll walk you through it. What happens is the application on the left-hand side decides to start a transaction. The broker allocates it to a transaction manager. The transaction manager recognizes that it has to load a list of atoms in order to do the work that it has to do. It goes to the archive manager and collects those atoms, does the work, and hands back the results. Pretty straightforward, nothing about that sounds very interesting, and it's certainly similar to things you've seen before. But let's see what happens if you add a second transaction manager. Remember the step function that we showed you? If you add a second transaction manager, we saw what happens. The performance goes up, and in some cases goes up more than linearly. Why did that happen? Well, what happens, a second transaction manager enters the fray. At first, it's not very busy at all. In fact, it's doing nothing. One of the brokers notices that it's there, and it hands it some work. And just like the first transaction manager, what it's going to do is, in order to do that work, it has to get its list of atoms together. It'll go through that list of atoms, do the work that it was asked to do, and hand back the results. The reason that it went a little bit faster than 100% faster was that some of the atoms that it was loading, it didn't have to load from the archive manager. It noticed that they already exist instantiated on the first transaction manager in memory. And so it fetched replicas from there. And that's a very fast operation that takes just 100 microseconds or so to do that. And so it's much, much faster, orders of magnitude faster than going to the disk to do it. And so you can get nonlinearities in the system where it goes faster than twice as fast. Obviously, the first thing that comes to mind is what happens if one or both of these transaction managers start changing that replicated atom. You've got atom number, let's say 123, which exists on both of these transaction managers, and one of them or both of them starts changing that atom. How is that handled? Well, the traditional way to handle that in a database is to have a thing called a network lock manager, which synchronously locks the data on both machines and allows only one of them to update it, and we're very familiar with that architecture. What we know about that architecture is it's synchronous and it doesn't scale. What we use instead is an asynchronous mechanism based on something called MVCC, which is a version management mechanism invented by Jim 25 years ago. It now exists in most databases in some form or other. We have a sort of a turbocharged version of that. And how it works in simple terms is that we never actually ever delete a record or do a destructive update to a record. What we do is create a new version of the record pointing at the old version of the record, and it's our job to manage the housekeeping that says who sees what version of the record when. And that's the basic mechanism that we use for doing both concurrency management and consistency. Quite a complex topic, and in fact is the central and most complex topic of the whole system, because that's the heart of why it's an ACID database. but it's worth taking away at least that it's an asynchronous mechanism that's heavily based on version management. I mentioned that you could add the transaction managers. Well, what's interesting is you can actually add archive managers as well. It's a little bit more complex. The transaction managers are diskless. I think I said that. And so adding one doesn't require you to do anything in terms of stored data. The archive managers is where the data is stored, and if you add a second one, obviously it has to copy the data. I want to be clear up front that it's not a partition. We're not talking about Archive Manager 1 having half of the database and Archive Manager 2 having the other half of the database. This is done in order to give you redundancy, and so both Archive Managers have the entire database. When you add the second Archive Manager, if you add an empty Archive Manager, it's going to spend some time catching up before it actually takes part in the database system. It's obviously smarter to first clone the first Archive Manager before you add the second Archive Manager. And if you clone it and then add it, it's got less catching up to do. It will catch up to the system, join in, and take part. I'll note that it does increase performance. Obviously, you get a multiplexing effect, and the transaction managers are going to fetch atoms from the most responsive place they can get it from, which is going to cause there to be a load balancing between the two archive managers. So you get a performance improvement by doing it, but it's not based on partitioning. It's just based on the fact that you've got more places to go and get the data from. I'll also mention that the archive managers, once they're both up and running, are peers of each other. So if one of them goes away, it doesn't matter which one, the database system keeps running. So it's true redundancy. You don't get that with traditional database systems. And you guessed it, obviously you can keep scaling. I showed you this thing running with 9 transaction managers. You can keep scaling that, and you can add them dynamically. That's part of how it works. Additionally, I mentioned that the archive managers need not all be the same. The default one runs on top of your file system, and by the way, we don't care what file system. It can be your local file system, it can be a SAN, it can be whatever you want it to be. But it also runs on top of other things, including S3, which is a key value store on the Amazon cloud, and that's the core storage of the database system. And I mentioned Hadoop HDFS here. There are other things that we're going to be supporting over time. We don't really care architecturally. The system doesn't mind what you use, as long as it's something that knows how to store data, get data back, and delete data. One other knock-on effect of this architecture is that it's very hard to stop. With traditional databases, you care about what's the failover mechanism and how do you handle those kinds of high availability issues explicitly. There's no explicit management of high availability in NuoDB. Essentially, you can kill nodes and the system keeps running. In fact, to stop the system from running, you're going to have to take out an entire tier, either all of the archive nodes or all of the transaction nodes or all of the brokers. If at any point you've still got one broker, one transaction manager, and one archive manager running, the database is still running. And even if it does go down, restarting it against an archive manager is really quick. So if you wanted, you could put one of these archive managers under a bunker in Montana or somewhere, and if the entire database goes down, you can hook up a blank transaction manager to an archive manager very quickly and get the whole system up and going very fast. So this is a system which has a kind of a resilience to failure rather than a failover mechanism, but it's an extreme resilience to failure. There are a couple of slides here about how we can run multiple databases on the same cloud. We talked about that being a very important thing. We're very interested in customers that are running perhaps hundreds or thousands of databases and wanting to do that very efficiently. The system does that very naturally. And this really just depicts how that happens. And what I'm going to do is to simply declare that you can see the different colors referring to different databases. They can overlap on the same machine. They can have dedicated machines. They can run across multiple machines. And you can imagine how all of that works. Let me also then say, we did mention before geo-distribution, and what we mean by that is running in multiple data centers at the same time. Of course, because the communications between these atoms are asynchronous, we don't really have a great sensitivity to the latency between these different data centers. Therefore, we can run across a WAN. As long as we've got the bandwidth to do it, we're going to be pretty okay. And so in this kind of configuration, you'd probably have 2 archive nodes in each location, and you would have as many transaction nodes as you need in each location, and it would be one database running in multiple data centers at the same time. Most of the communications will be happening locally. Communications that have to happen remotely will do so, but they'll happen asynchronously. Of course, if Godzilla rises up and eats one of your data centers, that's okay. The system keeps running in the other data centers. There's no failover, there's no wait, there's no disaster recovery, slave systems that you have to switch over to. It just works. The product today is in beta release. It's in its 4th beta, and very shortly we'll be going to its 5th beta. It's a full SQL 92 implementation with 99 extensions. It has all of the standard SQL APIs that you would expect, JDBC, ODBC. It supports Ruby Active Record, it supports Hibernate, it supports a number of other ORM systems, and we'll keep extending that. It's relatively straightforward for us to do that. Indeed, some of our customers are helping us to do that on an open source basis. We support Linux, we support Windows, we support Mac, and that seems to be a broad enough platform support at the moment, but again, it's easy for us to support more. Usually we're finding with our beta program that's the range of platforms people care about. But we also run on public clouds, and so we'll run on EC2, we'll run on Rackspace, we'll run on public clouds, we'll run partially on public clouds and partially on your own machines if that's what you want. It's really not a big deal because the system doesn't really care about the latency between the machines. And I mentioned that archive nodes can have multiple implementations. They can have multiple implementations in the same system at the same time. The default one is a file system implementation. We also support Amazon S3. Layered on top of that, we have various commit protocol semantics, and that's a whole other topic which we can layer on top of this so that you can have lots of choices in terms of trade-offs between performance and security of your data. Those are just configuration options in the system. We support lots of standard SQL tools. If you have ones that we don't currently support, we'd be interested in talking to you. Let us know and we'll take a look at them, and usually that's just a few hours work to get those going. And we have a whole bunch of advanced features. I don't have the time to go through those now, but they're things that we've learnt over decades actually of building relational database systems. There are a bunch of things you have to have that really make databases very useful as opposed to interesting. And I'd just like to conclude with saying that we're in Beta 4 release. Beta 5 is shipping soon. We've got over 80 organizations that are in the beta program today. That number is growing fast. We'd love to have you on board. If you've got interesting applications that you'd like to apply this technology to, please give us a call. Go to our website, sign up for the beta program. We'd love to talk to you.